So this was what we did last time. Okay, we did that you have what was happening. You had a weak acid, okay, and I told you it partially dissociated, and it produced two things. Any weak acid is going to, whether it's a diprotic or a triprotic acid, it's going to dissociate and it's going to produce one H plus one ion. Okay, so there is dissociation happening for all sorts of acids. And therefore, they have a dissociation constant, which is product concentration. It's an equilibrium reaction. So when an acid dissociates, it's an equilibrium reaction. So your equilibrium constant is your product concentration, which is this, okay, divided by your reactant concentration, which is this. So that's your expression. And what happens is that these two ions have equal concentration. So these two ions have equal concentration. So your expression, your numerator, could be written as just H plus 1 squared. Instead of writing X minus 1 and H plus 1, because both of them have the same concentration, you can just write it as H plus 1 squared. So for a weak acid, this expression turns into this expression. It's H plus 1 squared divided by the acid concentration. And this is then your overall expression. Anyways, dissociation constant, your equilibrium constant, if it's large, that means it's a strong acid. That means there's more dissociation happening. More of these ions are getting produced. And if it's small, that means it's a weak acid. So every weak acid has a dissociation constant, and it is described by its dissociation constant. Every weak acid is going to be described by its dissociation constant. So you will not be able to figure out what the H plus 1 concentration is unless you know what the dissociation constant is. You can remember we have to figure out what the H plus 1 concentration is. That's most of the questions are going to be about that. Okay, so what I'm going to do is I'm just going to open the worksheet and we'll try and एक second. अच्छा, so this one. अच्छा, so we're going to try and solve questions just about the dissociation constant. I'm just going to pick the simple questions first. अच्छा, so here's our worksheet. So you can see over here that every weak acid, they've given their dissociation constant. We're not going to do this question. This is a slightly more complicated question. Just the ones, yeah, we can try this one. So for example, they're talking about phenolphthalein, right? And this is your typical weak acid dissociation, that it produces an H plus 1 ion and it produces whatever negative ion it's going to produce. This is going to have a dissociation constant, which is going to be product concentration. That's H plus 1 concentration. And there's something called ion. We don't know what that is. Divided by your acid concentration, which is H ion. So I've got my expression. And what they're asking for is they've told us the Ka value. The dissociation constant value is given. So we know this is equal to what? 5 times 10 to the power minus 10. And remember, most of the time, this value is going to be small. Why? Because they're all weak acids. So since they're all weak acids, they are not going to produce a lot of ions. They're not going to dissociate. So it's got a weak value. It's got a small value. Anyways, they've given us the pH as well, which is 8.8. You can remember what pH was. We did a lot of practice for that. What is pH? pH is the negative log of the concentration of H plus 1 ions. And I told you that if the pH is 8.8, that simply means that your H plus 1 concentration is 10 to the power minus 8.8. You get that's 10 to the power minus 8.8. I'm just going to one more time just explain pH once more. What was pH? What was negative log? Log expresses, if you have 10 to the power minus 3, if you take log of this, that's going to give you -3. And since we're taking negative log, you're going to get +3, right? So that is what pH. It's the negative log of the concentration of H plus 1 ions. So when you see 3, that means it's 10 power -3. So when somebody says pH is 8.8, that means the H plus 1 concentration is 10 to the power -8.8. You can keep that in mind. Yemne, we did a lot of practice for that. Now, the next thing is, so in this expression over here, I know that H plus 1 is 10 power -8.8 because they told us that the pH is 8.8. So it's ion -1 concentration divided by HIN is equal to 5 times 10 power -10, right? And they're looking for this ratio over here, which is basically I just need to take what I just need to do is I just need to take this to the other side. So I'm going to take that to the other side and I'm going to get the ratio. So it's 10 power -8.8. Can somebody try this on the calculator? What do you get? Hala, Minal, Umar, can you try and solve this?
0.315.
0.315.
315.
Okay. But is this clear that this was what your K expression was? And I'm just going to repeat the question. They gave us K, they gave us pH, which is why we also knew the H plus 1 concentration, right? And so since these two were given, uh, so I was able to figure out what ion -1 and HIN ratio, which they were looking for, what that value is. Okay. So let's try and do another question just about K. 1 second. ये सारा तो KSP है. Yeah, this one. See, again, they've given us that HOBr is a weak acid, right? So that means if you have HOBr, it's a weak acid. That means it's going to be an equilibrium reaction. It's not going to fully dissociate. It will produce H plus 1 ions and what is left, OBr -1. Okay, so it's going to dissociate like this. It's going to have an equilibrium constant, and they've given us the value of that equilibrium constant. So it's H plus 1 concentration times OBr -1 concentration divided by HOBr. I mean, you don't have to do this all the time because I already told you that your expression, these two ions have exactly the same concentration. So your expression would be K is equal to H plus 1 squared divided by the acid concentration, which is HOBr. I said, but anyways, your K value is given. So वो कितनी है? That's 2 times 10 power -9. Your pH is also given. It's the pH is 0.2. So that means your H plus 1 concentration is 10 power -0.2. So I know that my H plus 1 concentration is 10 power -0.2, and that's getting squared and divided by the pH के पूछ रहे हो. Calculate the pH of अच्छा sorry, that's वो गलती कर दिया. I misread it. 1 second. I mean, they obviously did not give us the pH. They were asking for the pH. This is not the pH. This is the concentration of the acid. So we didn't know what H plus 1 was. They actually gave us the HOBr concentration, which is 0.2 mole per dm cube. To figure out what H plus 1 is, like if I rearrange everything, it's 2 times 10 power -9 times 0.2, and it's going to be under rooted. Okay, make sure you put a bracket when you're doing that. And once you've found H plus 1, what you're going to do is you're going to take the negative log of that to figure out what the pH is. So can somebody do this? What do we get? Rumesa, Umar, Minal, what are we getting? और ये क्लियर है? हाला, इज दिस क्लियर? प्रोफेसर, इज दिस क्लियर? मिनल, इसाक?
Yes, sir.
Yes.
अच्छा, वैल्यू क्या है ये? मिनल, क्या वैल्यू आई है?
2 times 10 power minus 5.
नहीं, वो H+1?
Mm-hmm.
नहीं, वो फिर माइनस लॉग क्या है? बिकॉज ही वाज लुकिंग फॉर द पीएच। I mean, take the log and just change the sign.
4.7.
ठीक है, so you're getting 4.7. ठीक है, that's your final pH. अच्छा, anyways, इसको skip this one. We just focus on the key questions. Hmm. अच्छा, so over here, we can try this one. Again, it's the same equation. You got a weak acid, it dissociates, produces H+1, and it produces, I mean, some other thing, right? So you're saying the ammonium ion is a weak acid. Okay, the pH of a 0.3. So we know that ammonium has a concentration of 0.3 mole per dm cube. I mean, that is known. And the pH is also known. I think the pH, yeah, they've given us the pH, that's 4.89. So if the pH is known, that means the H+1, that's the first thing he's asking. What's the H+1 concentration? So if the pH is known, then it's pretty simple that the H+1 concentration would be 10 to the power minus 4.89. So what is that? What is 10 to the power minus 4.89?
1.28 times 10 power minus 5.
That's minus 5. And then he's asking for pK. I'm going to come to pK in a moment. We're going to find Ka first. What is the K expression? It's H+1 concentration times the ammonia concentration. But since both of them are going to have the same concentration, I'm going to write it squared, divided by the acid concentration, which is NH4+1 in this case. The K value, actually, they're looking for the K value. So the K value is 1.28 times 10 power minus 5. That's the H+1 concentration squared, divided by the NH4 plus concentration, which is 0.3. So that is what your K is going to be. What is it?
5.46 times 10 power minus 10.
So anyways, the last thing is that what is pK? P just stands for minus log. You can remember, I told you that the reason they go into log is that you're getting so many, I mean, these values are so small that they are hard to plot on a piece of graph paper. So what they do is they just go into log. So what is the log, negative log of this?
.3.
Yes, so that is 9.3. So that is 9.3. So यहाँ पे I'm going to add this, ठीक है, over here as well. Pk is just the negative log of Ka. So a lot of times they don't talk about Ka because of the fact that Ka values are so small. Okay, it's kind of difficult to actually communicate. अच्छा, मेरा एक second वो disconnect हो गया. Just 1 second, my tab is disconnected. Hold on a second. he gets connected. So anyways, pK is minus log of K, and I explained to you that question. Yeah, this one. So I already explained to you that these numbers are so small that if you take negative log, you get a nice whole number, which is like really nice to write and to plot as well. So saying or communicating 9.3 is a lot easier. I mean, this thing is like too small to write. But there's one problem with this, and that problem is you have to understand this, that the problem is that if K is large, right? I told you that the acid is going to be a strong acid. There's going to be more dissociation if K is large, right? You're going to have more products if K is large. But the thing with negative signs is that if you put a negative log or if you multiply anything by a negative number, what happens is that like if you have two values, right? 3 and 5. 5 is the bigger value, right? But if you multiply something with a negative sign, then the bigger value actually becomes the smaller value, and the smaller value actually becomes the bigger value. In between these two, 3 and 5, 5 was the bigger value. But if you multiply anything with a negative number, then the smaller value actually becomes the bigger value, and the bigger value actually becomes, well, the minus 3 is bigger than minus 5. So the problem with taking negative logs is that if K is large, that would actually mean that your pK would come out to be, it would come out to be small. Okay, which is why your pH scale is the other way around. The lower the pH, the more acidic it is, right? It's because of this negative sign. So always remember, if you have a strong acid, its Ka would be large, but on the other hand, its pK would come out to be very, very small. Okay, for example, if K is 1 into 10 power minus 10, then your pK would come out to be 10. Negative log would come out to be 10. But if your K is large, right, 1 into 10 power minus 5, let's say, then your pK would actually come out to be small, right? This is a bigger number. 1 into 10 power minus 5 is a bigger number. 1 into 10 power minus 10 is a smaller number, right? But in terms of log, in terms of negative log, 10 is actually a bigger number. So it's the other way around, okay? So is this clear that Ka large means that your pK would come out to be small? So for strong acids, Ka would be large, but your pK, the negative log of the same value, would actually come out to be small. Is that clear?
Yes.
ये बाकियों को clear, Umar, Ala, is this clear? Isaac, Rumesa, is this
Yes.
clear?
Yes, sir.
So going back to the question, we're just going to do a few more K type questions, just K. I mean, there's a lot of things still left to do with K. KW, leave that. Uh, for example, over here he's talking about, remember I told you diprotic acids, they have two dissociations. They're going to behave as two different acids. H2SO4 is going to release 1H plus 1. Then it's going to become HSO4 minus 1. That is going to behave as a separate acid, and it's going to have a different dissociation compared to the first one. And then that thing will release an H plus 1. So he's talking about dissociation 2, which is this one. So he's asking you to write the expression. So the expression is, it's H plus 1 concentration times SO4 minus 2 concentration divided by the HSO4 minus concentration. Okay, what is this? It's yeah, he's again asking for the Ka of benzoic acid. So you can either, do the whole thing, or you can just write the expression, which is K is equal to H plus 1 squared divided by the acid concentration. Okay, I'm not going to derive the whole expression again. I know what the expression is. The pH is given, that's 2.9. So that means your H plus 1 is 10 to the power minus 2.9, and that's getting squared. And my acid concentration is also given, that's 0.25, 0.025. Achha, jaldi se quickly tell me what the K value is.
6.3 times 10 to the power of negative 5.
6.3 times 10 power negative 5. Okay. So we got that. Anyways, there won't be any more interesting questions just on K. A lot of them. Okay, so we're gonna move to the second part of K now. Okay, I hope everyone's what K is, it's clear. Okay, it's perfectly clear. Now we're gonna switch to the next thing that we're gonna do related to K. And that thing is, that's called a buffer solution. And that uses the same exact expression. But it's slightly more confusing. So what's a buffer solution? It's a solution. The first thing they're going to ask you is they're going to ask you for the definition of what this is. So it's a solution that resists a change in pH. A change in pH when a small amount of acid when a small amount of acid or an alkali or a base is added to it. Now remember, when we started, I told you that all reactions are happening in water, and water has H plus 1 ions and it has OH ions, and they have a certain balance. If it's acidic, you're going to have more H plus 1 ions. If it's basic, you're going to have fewer H plus 1 ions and more OH ions. And I told you that reactions are very sensitive to this. Some reactions, they happen more quickly if you have more H plus 1 ions. Some reactions, they happen more quickly or easily if you have more OH ions, right? So every reaction has its own preference. Now, the trouble is that your pH, or this balance between the H plus 1 and OH ions, it should not change. Okay, for example, your digestive enzymes work best in highly acidic pH. That's why your stomach is very, very acidic. So these work best in acidic environments. So that means your stomach is trying its best not to change the pH, because if it changes the pH, your enzymes get denatured. They will stop reacting the way they should react. Sometimes they might even break down, right? So buffer solutions are, all natural systems are by default buffer solutions. Your blood, the pH of your blood should not change. If it changes, reactions that were supposed to happen will not happen, and reactions that were not supposed to happen, they will start happening, right? So the point is that all reactions around you in living organisms or anywhere else, they are very, very, मतलब हल्की सी acid rain होती है, तो plants stop growing, right? So the pH has to be maintained at all costs. So natural systems, what they do is that they're normally composed of, so what a buffer is made up of is, it's made up of a weak acid plus its conjugate base. So it's kind of a mixture of the two things. So it's a mixture of both these things. An example is you've got ethanoic acid. What is the conjugate base of ethanoic acid? That's ethanoate ions, right? That's the conjugate base. Hopefully that thing is clear to everyone that this is the acid that loses the H plus one. That's the conjugate base because it's going to accept the H plus one back again, right? So you've got a weak acid and you've got its conjugate. So you've got its conjugate base. Now, in your solution, both things are going to be mixed together. So if I have a container and there is the conjugate base and there is the weak acid, both of them are mixed together. And I'm going to add, let's say I'm adding H plus 1 to it. I'm adding an acid to this solution, right? The solution has a certain pH. So the acid that is added is going to be neutralized by the conjugate base, which is this one. What's going to happen is that the H plus 1 is coming in. So the conjugate base, which is obviously a negative ion, that's going to accept it and it's going to combine with it. So the conjugate base is going to get activated. It sees the H plus 1, grabs it, and that is what a base does basically. And becomes ethanoic acid back again, right? So the H plus 1 gets neutralized. Is this thing clear that you added acid to it and the conjugate base went in and accepted that H plus 1 and neutralized it? Is this clear?
Yes.
So vice versa, if I add an alkali to it, what's going to happen now? So if an alkali is added, it's going to be neutralized by the acid now. Okay, so this is the thing that's going to be acting as the acid. So ethanoic acid is capable of releasing an H plus 1 ion. So OH ions, it's a negative ion. It's capable of accepting an H plus 1 ion. So ethanoic acid is going to release an H plus 1 ion. It's going to become ethanoate ions, and the H plus 1 is going to go and combine with the OH ion, and it's going to neutralize it. It's going to turn it into water, right? So your H plus 1 was neutralized by the base, and your OH ions are getting neutralized by the weak acid. Okay, so this solution is kind of behaving as a buffer because it's got a base, plus it's got the acid as well. Okay, is this thing clear?
Yes.
ठीक है, Umar, Hala, Isaac, Romesa, is this clear?
Yeah.
So they're going to ask you to write these equations as well. Okay, how is this acting as a buffer? Okay, but it can only do that because it's going to. I mean, you can't add too many H plus 1 or OH ions because eventually at the end of the day you're going to run out of ethanoate ions and you're going to run out of ethanoic acid. So you can't add too much. I mean, like your stomach. I mean, you're always eating something, right? A lot of times you're drinking carbonates, which are basic. So your stomach pH is going to resist that. It kind of because it's got both things. It's got weak acids. It's got conjugate bases. It tries to neutralize anything that's coming into it. So that is what this system is doing over here as well. So this is what a buffer is. It's made up of a weak acid plus its conjugate base. It's a mixture of both. And that's what the definition of a buffer is. So, 1 second. So it's a solution that resists a change in pH when a small amount of acid or alkali is added to it. Now, the next thing is, then how is a buffer formed? I just told you that you need ethanoic acid. But the thing with ethanoic acid is that it is capable of producing or releasing ethanoate ions as well. Like if you just have ethanoic acid, let's say I have 0.1 mole per dm cube ethanoic acid. Well, automatically I'm going to have the weak acid, but it will produce some conjugate base as well. So if I just have the weak acid, only this thing, if I have a solution, just a vinegar, I have a solution of ethanoic acid, will it act as a buffer? Well, it can possibly act as a buffer because if this is 0.1 mole per dm cube, it will produce some conjugate base as well. But the trouble is that weak acids are very weak acids. They don't dissociate a lot. So normally if you just have ethanoic acid, there would be some ethanoate ions, but that it would be too less. Naturally, it's going to be too less. So the amount of conjugate base that is going to dissociate would be very less. So the problem is that ethanoic acid on its own is mostly just ethanoic acid. It has a few ethanoate ions, but it will probably not act as a buffer because it just has very, very few ethanoate ions. So what needs to happen is that you need to add a mixture, right? I mean, these are already there. So you need to add extra amount of ethanoate ions into the mixture. So how do you do that? So extra ethanoate ions are added by adding a salt. So you're going to mix some salt which has ethanoate ions. That needs to be there. Otherwise, on its own, this ethanoic acid is pretty much not capable of producing this conjugate base. So normally your buffers are going to be, well, it's going to be ethanoic acid. I mean, you're going to take ethanoic acid. Plus, you're going to mix it with the conjugate base. And where's the conjugate base coming from? It's coming from the salt of the same weak acid. So it's your weak acid plus the salt of the weak acid. Right? So is this minor point clear that if you want to make a system and turn it into a buffer solution, it can't happen on its own. You can't just add a weak acid and it will produce ethanoate ions. These ions have to be added from outside. And the way they're added is that you will add a salt of the weak acid. Is this thing clear?
Yes.
ये बाकियों को clear हाला मैं सब Isaac Umar, is this clear?
Yes.
अच्छा, so now what's last thing? Remember your expression. It's the same equilibrium, right? It's the same ethanoic acid dissociating, producing these two ions. So it will have the same dissociation constant, except with one difference. And that difference is that since you're adding extra of ethanoate ions, these two ions are not going to have the same constant. I mean, they're not going to have the same concentration. Pehle kya tha? When you just had the weak acid, what were we doing when we just had the weak acid? I told you that the two products, the products that are going to be formed, the two ions that are going to be produced, they're going to have exactly the same concentration. But the trouble now is that this conjugate base, extra amount of conjugate base is being added to the system. So these two ions are no longer going to have exactly the same concentration. So that's the only difference. So if I write my K expression now for, let's say, ethanoic acid, it's the product concentration. I mean, it's exactly the same expression. And the K is a constant only, so its value is not going to change. It only changes equilibrium constants. They only change with temperature. But these two no longer have, I mean, the products no longer have the same concentration. So instead, your K expression now is, it's your conjugate base or salt concentration times your H+1 concentration divided by your acid concentration. Okay, so your expression slightly changes, very slightly changes. So you got a weak acid, you got its salt, right? This ion is coming from the salt. And that's your weak acid. Okay, so your expression very slightly changes a little bit when it is a buffer solution. And you can't use H+1 squared anymore. Okay, so is this clear? Is this minor thing clear? That your K expression has slightly changed a little bit. Is that clear?
Yes.
Yes.
Good. Okay. So tomorrow we'll do questions on this. This is going to be complicated, okay? Because they're going to ask you. This is going to be complicated. You're going to see the questions are going to be slightly more complicated, okay? So we'll do this tomorrow then. Simple K question, that's pretty easy. Buffer solution questions slightly complicated. So we'll try and cover that tomorrow then, okay? Okay, everyone. I've shared the worksheet as well. We'll go through questions on the worksheet, okay? Take care, Allah Hafiz.